Hi, welcome back to lesson 3 on regression analysis. In lesson 1, we learned how to conduct regression analysis with continual variables, and in lesson 2, we learned regression analysis using categorical variables. In lesson 3, we're going to pick up from lesson 1, and you can apply this to lesson 2 as well. But what we are actually interested in this lesson is to generate the actual predicted values from linear regression models. When we run linear regression models, what we actually get is the unit increase or decrease in the outcome or dependent variable depending on an increase or decrease in the independent variable, but we don't get the actual predicted values. In other words, we don't get a set of numbers that tells us in the near future, with an increase or decrease in the independent variable, this is what you expect in the dependent variable. You only get the projected increase or decrease rate, right, which is the correlation coefficient. I'm going to show you how to generate the predicted values so you can include them in your data frame or your data set and conduct further analysis with it. An advantage of doing this is you can analyze these predicted values separately. For example, you can make histograms of these predicted values and you see how in the future the trend is going to be like regarding the outcome variable. Are they going to be assuming a normal distribution or whatever you want to do with it, right? There could be several analysis that you can do with these predicted values that you might not be able to do with just doing a linear regression model. So let's get into the lesson and see how this is done in R programming. In a previous lesson, we ran a regression model and then we named it LM test. I'll just call LM test and we see what we got in lesson 1. Okay, so in lesson 1, we had our intercept and we had our correlation coefficient. So we knew the increases in health expenditure if GDP per capita increases. I'm going to look at the summary statistics of my my independent variable once again, my GDP per capita variable. I want to know what is the lowest value and the highest value in my GDP per capita variable. So the lowest value in GDP per capita variable is $188. Probably these are some of the world's poorest countries. And the highest value in my GDP per capita variable is $85,868. And this is obviously one of the richest country, or maybe the richest country in terms of GDP per capita. The reason why I did this is I'm going to generate these predicted values from the values in my independent variable. Remember, we have some values in the independent variable and we want to generate values of the outcome variable depending on how the independent variable looks like. And this is the same thing happening in your linear regression model, but the linear is happening at the background of your linear regression model. You don't see it. So this is how you get to see these values happening in the background. The next thing I will do is I'm going to create an object called explanatory data, and in this object I assign the range of values for GDP per capita to a function called table. The table function arranges data in a data frame and it's part of the tidyverse package. So I'm interested in every value inside my GDP per capita. Using this semicolon, as we have learned, is just telling R that give me everything between the lowest value and the highest value. If I run that, I now have an object called explanatory data that has my actual values that I want to use to make the predictions. The next thing I'm going to do is I'm going to use a function called predict. Now the predict function, as the name goes, will give me the predicted values, or what I think is actually happening in the background of a linear regression model, right? The predict function takes on two arguments: the linear regression model that you run, and the second argument it takes on is the actual values that you just generated. If we run this prediction, we get a lot of data, right? We get a lot of data that shows the actual predicted values of health expenditure. So this is telling you that depending on each of the values in GDP per capita, this is how much countries will spend on health. But as you can see, this is too clumsy. Like, we want it in a data frame. If we want to generate these predicted values in a data frame and make it look nicer, we need this line of code. We create an object called prediction data, and we assign to prediction data an explanatory data which we generated using GDP per capita. So explanatory data has our GDP per capita inside, and we pipe it, so we connect it to a whole new function altogether called mutate. Inside our mutate function, we have health expenditure, and we are saying that health expenditure is equal to the prediction that we generated previously. Remember, previously we generated a prediction which was the linear model and our GDP per capita variable called explanatory data, right? But it was too clumsy. So we are assigning this whole clumsy data set once again to the spend health variable, which is the actual outcome variable. But this time we are asking mutate to take it and arrange it nicely and add it to an object called prediction data so that we can present it nicely. When we run this line of code and we call prediction data, we see that it looks better. So now we have our independent variable, which is GDP per capita on one side, and then we have our health expenditure on the other side. We're able to predict that with each increase of GDP per capita, this is the equivalent health expenditure amount that we should expect. Now, this is not in the actual data set. Remember, in the actual data set, we have what is happening in the real world, which is 187. Maybe from 187, the next value is 190 or 250. But with this, we're able to predict that at each increase in our independent variable, this is the increase in the dependent variable. So in other words, this is what the linear model was trying to tell us. The linear model was trying to tell us this, but it was only giving us the rate of increase or decrease, whilst this approach gives you the actual values that the linear model is not telling you. With this, we can go ahead and do even further analysis with these predicted values. Aside knowing what the linear model tells us, we have the actual predicted values for further analysis. Thank you very much. Please subscribe if this video is helpful for you. In the next lesson, we're going to talk about extrapolation. See you.